Lesson 10.4, determine concavity / inflection points algebraically. We're given a function f of x, find all intervals on which f is concave up. So what we've learned is that concavity comes from that second derivative. And concave up is specifically where that second derivative is going to be greater than 0 or positive. So to be able to do this algebraically, I'm going to have to get the second derivative of this. So first derivative, 6 times a 6, the 6's would cancel to get x to the 5th minus 10x to the 4th plus 20x cubed. Easy enough. Second derivative is 5x to the 4th minus 40x cubed plus 60x squared. Now I've got to find these critical points of my second derivative. Critical points are where the derivative equals 0. So I'm setting this equal to 0, and then this is just something that needs to be factored. Always look for a GCF. I see every coefficient can be divided by 5, and I can take out an x squared. So that's my GCF. I would have left an x squared minus 8x plus 12. Then I need to factor this basic trinomial. I need two numbers that multiply to make a positive 12, but add to make negative 8. Going to have to both be negatives, and that would be 6 and 2. So then my critical points come from each factor. Anytime I have a monomial set equal to 0, I'm going to get 0. Because I'm dividing 0 by 5, that's 0, squaring 0, 0. This gets x equals 6, and this is x equals 2. So then what I want to do is make a sign chart, and since this is a polynomial with no domain, I'm going to put arrows on each end because it'll go to the left and to the right forever. Negative infinity, positive infinity. I'm going to put my critical points on here in order least to greatest, so I'll have my 0, my 2, and my 6. Okay, so now what I've got to do is start plugging in numbers within these ranges and see if I get a positive or a negative value out of them. I'm going to teach you a quicker way. I always start on the right to get the first one going, so let's pick 7. 7 minus 6 would be a positive, right? 7 minus 6, that's a positive, times 7 minus 2, that's a positive 5, and then 5 times 7 squared, that's a positive. So positive times positive times positive is positive. I don't really want to do that for every single one. So I'm hoping you remember multiplicity. Multiplicity refers to how something gets graphed. And so what's going to happen, let's say I had x cubed times x minus 1 squared. This would have zeros at 0 from this guy and at 1. 0 and 1. It's going to cross through where this is an odd power. So when I have x cubed, it's going to cross through at 0. But when I have an even power here at 1, it's going to bounce. So it stays both negative. So see, I went from positive, cross through into negatives, negative, bounce back into negative. So what I can do on these is now I want to see what's happening at 6. So go back to the factor that got me the answer of 6. The multiplicity on this, if I don't see it, is 1. It's to the first power. That's an odd number. So it would be crossing through at 6. So whatever this side is, it's going to be the opposite. And then go to where the answer got 2. That would be this factor of x minus 2. It's to the first power, which is an odd multiplicity. So it's going to be the opposite of this. That means it crosses through into the positive. And then last is 0. Since this was x squared, it really has a multiplicity of 2, which is an even number, so it's going to bounce and stay in the positive. And so really this function is doing this, just so you know. It's positive at 0, bouncing, staying positive. At 2, it's crossing through. And at 6, it's crossing through. So bounce, cross. Just so you know, this is going to be your friend and get you the answer faster. And now it says which is concave up. Concave up is anywhere where this is positive. So that's going to be all of this and this. This interval would be saying from negative infinity to 2. And this interval would be saying 6 to positive infinity. All right, number 2. Given this function, find all x values where f has an inflection point. An inflection point is where the second derivative equals 0, but also must change signs. So it's a mistake to just say our zeros are critical points, or as critical points are inflection points. That's not true. We got to make sure it's changing from positive to negative. So go ahead and take the first and second derivative of this function, and we'll see if we get the same thing. Okay, that's what I ended up getting. I'm going to factor now because I want to be able to figure out where does this equal 0. I'm going to divide out a 2x. That would leave me with an x squared plus 6x plus 18. And then I'm going to factor this trinomial. Two numbers that multiply to make 18 and add to make 6 would be... Well, I made a mistake here. That's why I thought, oh, that does not work. This should be 9. And then that makes more sense. That would be 3 and 3. Or I could write this as x plus 3 quantity squared. That would help my multiplicity situation. So now I'm getting critical points at this gets 0 and this gets -3. Make a sign chart. Since it's a polynomial, put arrows on each side, put your critical points in order. Okay, I'm going to start over here on the right where it's positive. That's easiest for me to plug in. So let's say our number is 1. If I plug that in for x, 1 plus 3 is 4 squared, that's a positive, and 2 times 1 is positive. Easy enough. Then at 0, that came from this factor of 2x. Since x is to the first power and that's odd, I'm going to switch signs here, cross through at 0, going from positive to negative on the graph. And then -3 came from this x plus 3 factor, but since it's a multiplicity of 2, which is even, it's going to stay the same sign on both sides. Okay, and so my inflection point does not occur at -3 because my signs didn't change. It only happens here at x is 0.